Today we're continuing on with exponentials, and we're going to get a little bit more detailed about what is truly considered the parent function for these, but I'm still using air quotes if you looked at me when I said that, when I said parent function. Because for exponentials, there really is no parent function, but mathematicians generally agree that the one we're learning about today is like the parent function for exponential functions. Now, this is not something you would have ever learned about before, so it's going to be something new. It is called the natural base E, or the natural number. Now, I bet you're saying, Miss Quigley, that is a whole letter. I know. But y'all know how, like, pi represents a number? What is pi? Do y'all know? 3.14, yeah. Pi is approximately 3.14. E is also a number. So we've avoided using e's. I don't know if you've noticed this. In any of the math that you do, we use f of x, we use x, y, t, those sorts of things. We've never used an e because e represents a number. It is called Euler's number. Now I bet you're looking at this, you're saying, that looks like the word Euler. You're right. So Euler's number, again, looks like it's pronounced Euler, but it's pronounced Euler, is approximately 2.718. So just like pi, that number would keep going because it's not a rational number. It's considered irrational. We're never going to be able to write it like a fraction. It's always going to be some decimal point that keeps going, just like pi. Now this number, mathematicians studied for a really long time back in the day, and they realized that this number shows up a lot in the natural world, which is why it's called the natural number, 2.718. Now, we will never type the number e in. Like I know with pi, for a lot of times you use the number 3.14. That's an approximation of pi. Your calculator has a button for pi. Does anyone know where the button for pi is on the calculator? Do you see a pi anywhere on here? Look at the exponent button, the little up caret. What's right above the exponent button in blue? The pi. So our calculators had a pi button this whole time. Look at the button right underneath it. What's right underneath that button that says pi? Well, it's the divide key. What's above the divide key? E. So your calculator has a button for this natural number. So when we're going to be using it in the calculator, you're going to want to use second and divide to use the number E when you're using this calculator. If you are someone who goes home and uses Desmos, which 1000% is fine, on Desmos there's no button for it. You just type the letter E. Does that make sense? Because the number E in math is known to be this value, the same way pi has a value. Now, since it's a number, it abides by all of the rules for numbers that we've always used, which includes all of our mad spam rules. As a quick review, if we have the MA part of mad spam, what is that telling me? If I'm multiplying the bases, what do I do with the exponents? Add. If I am dividing the bases, what do I do with the exponents? And if I have powers raised to powers, what do I do? Multiply. Okay. So here's how we apply mad spam to the natural base, to the natural number. In this first problem, E is just a number. So this is going to be e to what power? Remember, we are multiplying here, so what does that mean we do with the exponents? Add them. So this is going to be e to what power? The 9, 3 plus 6. Now, e to the 9th power is a number. So we would multiply that out, but not in our heads because we can't multiply rational numbers in our heads. Like, take a lot of paper to do it. So if I was wanting you to multiply that out, you'd just type e raised to the 9th power in your calculator and give me that number. But we're going to leave it as e to the 9 because we're practicing exponent rules. For the second one, do you see how, again, this is all just numbers. I know there's a letter there for e, but e represents a number. We still are going to use mad spam rules. But we treat big numbers like we've always treated big numbers. So we have 16 divided by 4. What is 16 divided by 4? 4. And then we have the exponents, which is going to have me subtract them since we're dividing. So what is 5 minus 4? 1. Now, do I need to show that 1? No. And if on your homework, I'm pretty sure if there's supposed to be e to the 1. Don't put the 1, it'll count it wrong. But for me and on paper, you can put the 1 there, that's fine. All right, we've got parenthesis powers. This is the one where we're going to multiply. It feels like distribution when we do this because we have to multiply to every exponent. But we want to make sure that we're raising the power, the 3 to the power 2. So don't say 6. What is 3 squared? 9. I'm getting 9 because, again, I'm raising the big number to the power. Those rules have never changed. The rules that have changed are for the little numbers. Instead of raising negative 4x to the second power, I'm just going to multiply it by 2, which would make this e to the negative 8x power. Does that make sense? These are all rules we've kind of done before, so it should. What's interesting, though, oh, wait, we need to clean this up. Why didn't y'all stop me? What's wrong with this right here? It's a negative. Have I ever let you leave negative exponents in the answer? No, so does anyone remember how we cleaned that up, though? What did we do to get rid of the negative in the exponent? We flipped it, right? So what we're going to do is we're going to leave the 9 alone. The 9 did not have a negative exponent, but the e had a negative exponent. So I'm going to put the e in the bottom, and then I'm just going to make the power positive. 9 over e to the 8x power is the correct way to finish answering this question. Those are the same thing, but I like it to have positive exponents. But number 4 is a kind of problem we haven't really seen before. It's seen a lot with the natural base e, but we have this 4th root of a term. Now what we're going to do is we're going to remember some of our radical rules. And those radical rules said that we can split my radical into the multiplication problems themselves. So this is like having the 4th root of 16 times the 4th root of e to the 24. Do we see that I just kind of split the big number and then e by themselves? Well, the 4th root of 16 is a number. Do we remember how to type 4th root of 16 into our calculator? It's on the math screen. Math and then which number? 5. So everybody right now, type math 5 and then do the 4th root of 16. What do we get? 2. Very good. So we know that this is equal to 2. We just need to know what the e part's equal to. And due to a lot of math that I don't really want to discuss because I think I might confuse you, I'm just going to tell you what to do here. When you have a power inside here like this, all you are going to do is divide it by this index number. So you just divide the exponent by the index. So what is 24 divided by 4? 6. So this is actually just e to the 6x. All I did was divide 24 divided by 4 to get 6. So when you have these weird problems like this, where you still have a letter with an exponent, specifically e, so it's a number with an exponent, you're just going to divide the exponent by the index. Does that make sense? So it's really pretty easy, especially if you separate them into 2 parts like this. You're going to have a big number, and then you're going to have an e number. And you just divide the index. So this number e, like I said, it's going to sound weird for me to say number e, but it is a number, represents a really natural base for a lot of our exponential functions like we learned about last time to occur. Specifically, these are called natural base exponential functions. So their formula is going to be a times e to the rx power. Applying this to what we learned last class, the very first letter in the formula, does anyone remember what that stood for? Say again? Initial value, very good. That's still a thing. The number in the very front, the a value, is the initial value. Now, last class, we had parentheses with a number in the middle of it in this spot. When you're using a natural base, you will not really see the parentheses because E doesn't require me to put parentheses there, but that is still my factor, just like it was last time. Our factor in natural base exponents is the number E every single time. And since that number doesn't change, it's kind of hard to decide if it's going to be growth or decay, because last class we just looked at the number in the parentheses and said, is it bigger than 1 or less than 1 to decide growth and decay. But the number inside these parentheses, the factor all the time for natural base, is going to be E, which is 2.7. So instead, to decide whether something is growth or decay, you're going to look at the number R that's in the exponent. That number is going to show you growth or decay. And it really makes sense, the one that's each one. If that number up in the exponent is positive, do you think it's going to be growth or decay? Growth. Makes sense? If that number is negative, what do you think it's going to be now? Decay. So really it follows a lot of, it makes sense. A positive number in the exponent for natural base functions is going to grow. A negative number in the exponent is going to decay. So here's what the graphs might look like. We have our exponential growth with base E. For this one, because there is an invisible 1 in front of E, my initial value is at 1. So that is my y-intercept, 0, 1. This is the parent function, air quotes, for exponentials. We like base E as our parent function. And then if we look, every single time after this, the output is multiplied by that number E, 2.718. So this is going to grow at a very specific rate because of the E value there, because the base is always going to be E for natural base. But if we answer some more questions like we did last time, the horizontal asymptote, do y'all remember where that was last class? Where did I put, it was a purple line I drew on the screen. Where was the purple line every time? You could probably point at it, right? Wasn't it just like here? Yeah, that is going to be the same place that the horizontal asymptote is today. So when we draw that in, it's this invisible horizontal line that's at the bottom of the curve. Today still, my horizontal asymptote is at y equals 0. That won't always be the case, but for these basic functions that we're learning about, the horizontal asymptote is going to be 0. Domain represents all of the x values, and since there's nothing stopping my graph on the left and the right, there's no boundaries on the left and right, my domain is all real numbers, but there is a boundary on the top or bottom. Would you agree that this horizontal asymptote right here kind of bounds this graph on the bottom? It gives it a stopping point. So we have to talk about that when we talk about range. We say the whole graph is above that number 0, because it is. It has a bottom point of 0 that it's never going to touch. So that's what exponential growth with base E looks like. Obviously, the graph is going up, and it starts at the value 1. Those are the sort of things we need to see to graph it. Notice also that the exponent here is a positive number, meaning it's growth. On the other hand, if we look at the decay formula, what kind of exponent do I have? Negative. That means it's going to go down, which makes sense to me. Things that are negative should be going downwards, which is what exponential decay with base E is going to look like. For this formula, again, there's an invisible 1 in front of E, which is why my intercept is at 1. My initial value is at 1. Where would I find the horizontal asymptote? Same place. I heard you say it. Yeah, the same place. It still has not transformed this graph very much. We won't do that until like next class or maybe the class after. So my asymptote is still at y equal to 0. What's the domain here? Is there any stopping point on the left or right? No, the arrows go off screen, so what do I say for the domain? All real numbers. But isn't there a stopping point on the bottom of this graph? What number is the stopping point at? What number is this? What value? 0. So we just say that our whole graph has to be above 0 since 0 is the bottom of the graph. Does that make sense? So it's not really all that difficult to work with base E. It's just weird that E is a number. I get that. E represents a whole number, not even a letter. You may not have even noticed we've avoided using E's for your entire math career, but we totally have. So on the inside here on the first page, we're going to be working on graphing these natural base functions, and we're just sketching graphs of them because they're not as cute, air quotes, as the ones we graphed last time to do by hand at least, since we're not multiplying by like the number 2 or 1/2, we're multiplying by E. So what I need us to do though to make decent graphs here is we first of all need to know where this graph starts. What's the initial value here in 3e to the x? What's that first number? 3. So my initial value or my y-intercept is going to be at 3. So we can go ahead and put that dot on our graph. Check. We've got a good start. Last class when we did this, we just multiplied by 2 or divided by 2, essentially to make our other coordinate points. But this is not easy because we're multiplying by e, and that's not really something we can do in our head. But it is something we can do in our calculator. Can everybody right now, in their calculator, type in 3e? When you type in 3e with the natural number e, what does it give you? 8.15? Great. So what we're going to do is we're going to take 8.15 and we're going to make that our next coordinate point. Now 8.15 is kind of like, well, I'm just going to do my best. You're right. You're just going to do your best. You're going to make 8.15 your next output, which is about right there. And just because these are our notes, we want to make sure we know what we're doing here. We're going to label these coordinate points just for good measure. So we can kind of see that this is going to grow, correct? Mm-hmm. Now there's going to be a boundary on this growth graph. Where is that boundary? And what do I mean by boundary? I've been drawing it in purple every time. What is that called? Do we remember? Its initials are HA. Horizontal asymptote. For us today and until we learn about transformations, the horizontal asymptote is always the same boundary line. It's going to be here at the x-axis. Are you allowed to touch or cross the x-axis? No, it's an asymptote. So we're not allowed to touch or cross the x-axis, y equal to 0. With those 3 pieces of information, the 2 dots to show you what direction to climb or to grow, and the boundary, can we draw in this exponential growth function? I like to start at the y-intercept when I do this. Y'all watch on the screen for a second. I like to go from the y-intercept to the other point because it gives me a very obvious direction to go. Then I go back and do the opposite direction, and I just make sure that I get close to but never touch that horizontal asymptote. So when you are doing these problems later by yourself, what you're going to do is you're going to match up the y-intercept because it's a very easy point to look at. And then you're just going to decide if it's supposed to grow or if it's supposed to decay. That's going to be the way that you answer the questions for me that I'm going to ask you. You check this value, and you check if it's going up or going down. Now, how did I know this graph should be going up instead of going down? Very good. My exponent is a positive number. That means it's going to be growth. Let's write that down because that's kind of important. So we'll put a little arrow. We'll say growth because exponent is positive. That's a good conclusion to draw, that when our exponent is positive, our graph should be going up. We should get really familiar with these domain and range answers. What's the domain of this graph? All real numbers. There's no boundary on the left or right. Is there a boundary on the top and bottom? Big purple boundary, right? That's at the value 0, and our whole graph is above 0. So we say y greater than 0. Like literally copy paste those answers. It's been the same every time we've answered that so far. And it will be the same every time we answer this until we transform the graph in a couple lessons. So we can just memorize this for now. Okay, cool. We've graphed a growth function, a good little estimation. What if we do this next one? If we look at the equation, what kind of function is this one going to be? Growth or decay? Decay. Why? Because the exponent is negative. We're going to write that down because these are notes and we need to make notes like that for ourselves. Because the exponent is negative. When that exponent is negative when it comes to natural base functions, that's when we know it's decay. Again, this is different than last time. Last time we just checked the parentheses for a number bigger than 1 or less than 1. That still applies, but when it's natural base, we look up here. Okay, a good question here is, what's the initial value? 1. How did you know it was 1?
Because it doesn't have a number next to E.
Yeah, there's an invisible 1 there. If you don't see a number next to E, the number is 1. So my y-intercept is at 0, 1, and I know the first place on my graph. When I'm eliminating answer choices later on my homework, you look at the y-intercept and you cross off the ones that don't have the correct y-intercept. We also know that this is going to decay. So we really just need to know where our next coordinate point is. What I want you to try to do is I want you to fill in this formula with the number 1 right here. So what we're going to do in our calculator, just to get one more coordinate point, is we are going to type in 1e to the negative 0.5 times 1 power, because we want to see what's happening at the x value of 1. We're just plugging in numbers so I can get the correct direction. You should have gotten a very small number. What did you get? 0.6 some, right? Great. That means that my next coordinate point is somewhere right here at 0.6. Just do your best to graph it because I know we're human and we can't make perfect graphs. Does this make sense to me that it went down?
Yeah.
Why?
Because it's smaller than 1.
Because it's a negative number up there. So we know it's going to be decay anyways. We just need our boundary so that we can draw this graph. Where is the boundary? I think we all know where to point at it. We just need to know how to say it. You say at y equals 0. So when I say where's the boundary, you say at y equals 0. Very good. Yeah, that's the boundary line here. It's the horizontal asymptote, which means the graph will get close to but never touch it. So if we follow those rules, here's what it looks like. Starting at the intercept, you follow the rules, which means touch all the points but don't touch the purple line. And then you have to complete the curve. And we're just going to estimate the side we didn't give any points to. And this makes sense because it should be decaying. We're getting smaller. And it is. We fill in the rest of our information. What is the domain? And what is the range? Y greater than 0. Above 0, because it is. The graph is above 0. Yes? So you might be asking yourself, and if you're not, maybe ask yourself this question. We ended last class learning about compound interest, which was how money grows in banks or interest rates grow on loans or cars depreciate, those sorts of things. There is a connection between compound interest and the letter E. When we are using the letter E in our compound formulas, it's now called continuously compounded interest. So you will not see the words like quarterly, monthly, annually when we do continuously compounded. You're looking for this word straight up, continuously. This is the word you look for to know you switch and don't use the formula we used last class. you're going to use this one. Some of the letters are familiar, some of them are new. Just like last class, the A stands for the amount in the account at the end, so final amount. Does anyone remember what the P stood for? Principal, which is your initial value. Makes sense because it's the first letter, but yes, in money management, it's called the principal investment. This should be similar to last time. What did the R stand for? Rate. But when we used rate, did we use a percentage? No, we changed it to a decimal. We still have to do that. That's going to happen every time you do money management things. You always use a decimal in the formula. And then what did the T stand for? Time. And specifically time in years. That's how we do these sorts of things. So my question for you is, I highlighted a bunch of stuff in there, but what letter did I not highlight? E. Why do you think I didn't highlight E to give it a name?
Because it already has a number.
It's a number. It's always going to be that number. So we don't have to label it. It is the same Euler's number from the front of this page, 2.718. But we're going to use these things kind of the same way in the same problems like we did at the end of the notes last time with compound interest. This question number 7 says, a bank is offering you a rate of 9.8% compounded continuously. How much should you put away today if you want to have, I missed a few words there. Oh no, if you want to put away today to have $25,000 in the bank in 10 years. Okay, the number $25,000, is that A or is that P? Is that the amount I'm starting with or is that my final amount? Final. Okay, so when we fill in my formula, I'm going to put $25,000 in the final amount spot. Do I know the initial amount? No. So I'm going to leave P in my formula because I don't know what it is. We're going to have e to the RT power. What is R? The rate. But do I put the number 9.8 in there? No. What number do I use? 0.098. Very good. Remember, Dr. Pepper rule means that if you have a percentage and you want a decimal, you move the decimal 2 times towards the D, so towards the left. So we're going to have 0.098 in my exponent. And how, whoa, my voice just cracked. How many years are we saving? 10 years. So you're also going to have a 10 up in your exponent. Now, last class when we did this, it was just like beep, beep, beep. We typed it into our calculator because everything on this side of the function was numbers. Is everything on this side of the function numbers right now? No. What letter do I have left? P. Thank you for not saying E because E is a number. We need to solve for P. Now, don't mark this out because it's going to super confuse you. But if this was like the number 10, what would you do with the number 10 to solve for P? Divide. So what are we going to do with all that crazy stuff I just marked out? Divide. Okay, I need to rewrite it, so don't, oh good, it stayed. Oh great. So we are going to divide by all of that. So we do this, we say divide by e to the 0.098 times 10, but what I do on one side, I have to do to the other. Looks super weird. In fact, I don't love that I'm using a dot to show multiplication. I'm going to go back and change these to parentheses just because I think it will be clearer. Sorry about that. We know the little dot means multiply, but it started to look like my decimal and I was getting myself confused. So I'm going to use the parentheses. Okay, once I do this, this side cancels out. And what letter am I left with? P. When I'm left with P, I will have P equal to 25,000 divided by e to the 0.098 times 10. At this point, is everything on the right side of my equation numbers? This side. Yes, thank you for saying yes. E is a number. When we have only numbers in my equation, that is when I go to my calculator and calculate. We don't calculate too early in these because we will have decimals. You don't want to round a decimal too early. It makes your numbers, what's the word I'm trying to say? Like not as precise as they need to be. So right now in your calculator, make that fancy fraction. Do 25,000 divided by E raised to the 0.98 times 10 power. A lot of typing. I'll give you a second. The principal investment that I should start with to make sure I have 25 G's by the end of 10 years should be $9,382.78. Is that what you guys got, or we're going to get if I didn't give you enough time to finish typing? So what this is saying is if you find a bank offering you this interest rate continuously compounded, you put $9,382.78 in the bank today, leave it there for 10 years. When you look back at it, it will be $25,000. If anybody finds a bank doing this interest rate, I would really love if you would let me know because I will also be banking with that bank. Because in real life, the interest rates are not this good.
I doubt it.
Yeah, that bank would go like broke immediately.
Even if you pay like $10 each month,
yeah,
you don't have your money in there too.
Yeah, so it's like we gave you weird numbers just to make it look effective, but like this is how it works. Not with particularly these numbers necessarily. Okay, can we try another one? It's going to be a different kind of question as asking, but same continuously compounded formula. It says you have $500 and invested at 3% continuously compounded. How much do you have in 5 years? Okay, 500, is that A, P, R, or T? P, because we are principally investing $500. So when I get started, the number right here will be 500. It says it's continuously compounded at this rate. Ooh, 3%. How do we write that as a decimal? 0.03. So I know my formula is going to be E to the 0.03 power, but I want to multiply it by how many years? 5. So we just multiply it by the number 5. That means that all of these things are going to give me that final amount in this account. This time when we set this, okay, back up. Last time when we set this problem up, my variable was the P. So I had to do some solving to be able to type it in. What is the only letter I have left now in this formula? A. Thank you for not saying E. E is a number. Since A is already by itself and isolated and all of these are numbers, beep, 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 this is a calculator question, just like last time. Let's go ahead and type this in and see how much is in our account after 5 years if we have this investment.
It's 580.92.
580.92. That's probably more realistic for how a bank would pay you, because 3%, still really high. Well, really high is kind of too many adjectives. It's higher than banks probably give you, but this is a more reasonable amount of money. One thing I want to point out, and I think this will help with your 7.1 homework, if I were to change this question and not ask you how much money would you have in 5 years, but I ask you how much interest have you gained? Okay. How much interest have you gained is asking you, you started with 500, correct? How much more do you have now? Not how much is in the account by the end, but how much did you earn? So what could you do with this number, the one we have in the box, to figure that out?
Subtracted by 500.
Yeah, subtract your principal investment back out of it to answer this question. So you would take the final amount, 580.92, and you would subtract your principal investment, which was 500. 80.92 is the amount of interest I earned by doing nothing but telling the bank to hold my money. So make sure you know what the question is asking you. If it says how much is in the account, that's the final amount. If it asks you how much interest did you earn, it wants to know how much more do you have, essentially. Does that wording make sense in the difference between them? Yeah? Fabulous. I think that will really help us with one of the problems from our 7.1 homework that does ask that question. And that's all that we really have for 7.2 because it's essentially a continuation of last time with just a particular base E.